My name is Kat Gardner-Vandy, and I am a postdoctoral research fellow in the Department of Mineral Sciences, and I study meteorites. So when we look at the inner solar system, we see that basaltic igneous rocks are everywhere. On the surface of Mercury and Venus, we know from spacecraft observations that their surfaces are covered in basalts. On Earth, we have a lot of basalts, as many of you have probably seen firsthand. On the Moon, the dark regions, the lunar mare, are basaltic. On Mars, we know from spacecraft observations, rovers, and from meteorite samples that we have many different kinds of basalts. And in the asteroid belt, we also have many different kinds of basalts. This is a picture of asteroid 4 Vesta, which is one of the largest asteroids, and it has a suite of basaltic meteorites that we have. These basalts are characterized by a dark color. The minerals that are in basalts are dark, like pyroxene and olivine, and they're characterized by a low SiO2 or silica content. So although not quite as abundant, we also have rocks throughout the inner solar system that have a higher portion of SiO2 or silica. On Earth, we have rocks like andesites or dacite that are very light in color. On the Moon, we have the lunar highlands that are a type of rock called anorthosite, which is made of a very high portion of plagioclase feldspar. It's a very light color. And even on Mars, we have some rocks that are higher SiO2 content. Recently, the Mars Curiosity rover analyzed a rock called Jake M that is called a meteorite, and it's formed when you have an enriched magma source. So the key with all of these andesitic, or these very high silica rocks that are light in color, like I said, and then high in SiO2, is that they formed by really complex geologic processing. On the Earth, we have plate tectonics, and we have subducting plates going on that's necessary for andesite formation. On the Moon, we have a global magma ocean, or we did have a global magma ocean when it was forming, and so you have a lot of flotation cumulates that can get these lighter anorthosites. And on Mars, like I mentioned, you have these enriched and depleted sources that can give these meteorite type of compositions. So the take-home message here is that what we think now is that you need a very large planetary body that has complex geologic processes to make these highly silica-rich rocks. So you can imagine that planetary scientists were a little bit confused when a pair of rocks was found in Antarctica called Graves Nunataks, or GRA, 06128 and 129. Now we could see right off that these rocks were igneous, and they're also light in color. You can see in the upper right there one of the cut surfaces, and it's very light. So we can see that a very different geologic process happened here. Number one, the geochemical evidence shows that these are andesites, which is very strange for us to find in meteorites, since most meteorites are from asteroids. And we can also see in the geochemical evidence that these rocks actually were from an asteroid. They have a very early crystallization age. So we know it wasn't from a young planetary surface, it was from an older asteroidal surface. So this is a big mystery. How do you form an andesitic composition on an asteroid-sized body? So the most important clue that we have in order to better understand the formation of these meteorites is their association with a group of beautiful meteorites called the brachinites at the lower left. These rocks are olivine-rich residues that I studied for my dissertation, and I found that they formed by high degrees of partial melting of a very oxidized chondritic starting material, and I did partial melting experiments to prove this. So we know now that we have this association between the brachinites and GRA, so this begs the question, can we get both of them from the same source? Can we get them from a very simple type of melting on an asteroid? So the next step was to test this hypothesis and hopefully answer the question as to how GRA actually formed by doing some melting experiments. This is the fun part. We take that starting material, that original oxidized meteorite, and I stick it into a Deltec vertical tube furnace. On the left, we have the control panel, and on the right hand, this big igloo-looking thing is the actual furnace. And I cooked this sample, it was about 150 milligrams. I cooked it at 1100 degrees C for 4 hours in a gas mixture of carbon monoxide and carbon dioxide. And that gas mixture really sets the way oxygen is moving around in this system. And that sets the way we hope the mineralogy will end up after we've cooked this sample. When I'm done with the experiment, I can quench it in water and then pot and polish it and look at it in both the SEM and the microprobe here at the museum. So this is an image of the experimental charge that has been melted. There's a lot of the original structure here. Melting a rock at 1100 degrees C does not melt it very much at all, and that's what we were actually going for. So you can see I have labeled some of the minerals: plagioclase, olivine, phosphate. But the real key is what's in red, and that's the melt. So you can see a very fine network, very thin network forming around some of the olivine and phosphate grains. And that is actually some of the melt that was starting to form at 1100 degrees C. So I took this into the electron microprobe here at the museum and I analyzed it, and it's actually the exact identical composition as the bulk composition of GRA 06128 and 129. So this is a very exciting result. We were able to create the bulk composition of this rock using a very, very simple partial melting scenario. So the two take-home things I want you all to remember from today is that, one, our experiment did create a composition that's andesitic, that's identical to GRA 06128, 129. And the result here means that you can create rocks with an andesitic composition from very simple, low-degree melting on an asteroid-sized body. You don't require a large planetary scaled body with plate tectonics and water playing a role, or with the global magma ocean. You can do it very simply in the early solar system on an asteroid. Thank you.
It's really difficult to make an andesite on Earth. Why is it so bloody easy to make it in exotic meteorite?
Okay, so how is it so easy to make an andesite on an asteroid versus how difficult it is to make it on Earth? Well, when we think about what's happening on Earth, we don't have an original chondritic composition from the beginning. You have a mantle that's mostly olivine, you have this peridotite mantle, and so you have to get it from the crustal material alone. So here on an asteroid, you have the original chondritic composition. You have all of that highly volatile, rich phases like plagioclase, and then you can melt that right away to get the high SiO2 melts. So really, your benefit is having an originally chondritic composition versus a peridotite mantle, and then doing it really, really early in the solar system, as opposed to later on how the Earth is evolving andesites today.